16 or something. But I recently read that he didn't provide a proof. But it's following theorem. Pascal's theorem is it's Pappos' theorem for an interesting conic. So instead of two lines, as in Pappos' theorem, we start with an interesting conic. It's a projective theorem. We take 6 points, which we call P1, P2, P3, Q1, Q2, Q3. Okay? And now you do exactly the same as in Pappos' theorem. You connect P1 and Q2, P2 and Q1. And this is the intersection point S1, 2. P2, Q3, Q2, P3. And P1, Q3. P1, Q3, Q1, P3. Yep. Now we have 3 points. And you never guess what the theorem says. They're on the line. So if this conic is degenerate, consists of 2 lines, and if 3 points are on one line and the other 3 are on the other line, then you get Pappos' theorem. So Pappos' theorem is a kind of degenerate version of this theorem.
But is it degenerate in the correct sense that you can say it's so if you prove one, then you have proved the other?
If you prove this is the more general one. If you've proven this one, then you can get Pappos as kind of a limit case, but you have to work. It's probably easier to prove Pappos directly than to make all the details correct in this degeneration argument. But at least if you see this, you can guess the other theorem. Okay. So this is Pascal's theorem. We didn't prove it. So maybe it's a nice problem for the exam. Maybe it's a bit too difficult. What do you think? Too difficult?
Yeah. In the changing perspective document, there was the question whether it's only affine notions involved.
Okay. So yeah.
That was the question.
Yeah. So this is a nice test case then. So for this important thing to decide whether something is affine or projective, is this a Euclidean theorem? Yeah, it is. All notions are Euclidean, but in fact it's several Euclidean theorems. I think it's a theorem about an ellipse and about a circle and about a hyperbola and about
But this is drawn in projective space. So how could
that's
it...
drawn Blackboard.
Which is
But Blackboards, yeah, it's a magic Blackboard. Sometimes it's R2 and sometimes it's a projective K.
It just shifted to the universe.
Yeah. Okay. So let's start at the other extreme. The best thing would be if this were a projective theorem. The course is kind of jumpy. So we have to just to look at all notions appearing in this theorem. So we start with given an interesting conic. Is that a projective notion? Yes, it is. Given 6 distinct points on the conic, is that a projective notion? Yes, it is. Draw the line P1, Q2. Is that a projective notion? The unique line joining 2 points. It is. Construct a point S1, 2 as this intersection point. Is that a projective notion? Certainly. Then these 3 points S1, 2, and so on lie on the line. Is that a projective conclusion? Yes, it is. So it's a projective theorem. Yep.
Yeah, well, it's an interesting conic.
Yeah.
But do we need that it's an ellipse for the theorem?
Yeah.
Well, you say so, but
yeah.
Draw the conic board. That's and I don't know if
okay. So I can if I make the statement for a conic, an interesting conic, then it is a projective statement. Mm-hmm. Yeah. I could also make the statement for the ellipse. That's a more special statement. I have a more restrictive condition, I have the same conclusion. So then I get a weaker statement because I have a more restrictive condition and still the same conclusion. So, yeah, okay. So I could do that, and then I would have an affine theory. That would be kind of a lose-lose situation because I have a weaker statement, which is no longer projective, so it's more difficult to prove. So you can make life much easier by guessing that maybe it's true generally in projective geometry. And we're still talking about statements and not about theorems. So let's make the projective statement given an interesting conic and so on and so forth. That's a projective statement. If I want to prove it, I can choose any line as the line of infinity and get an equivalent affine version. So I choose a line here which doesn't intersect in the x theory, which doesn't intersect the conic. Then then the conic becomes an ellipse. And I get an equivalent statement about an ellipse. So the statement about an ellipse is equivalent to the projective statement. So I know, using projective geometry, even if I do not know whether it's true or not, if it's true for ellipses, then it's also true for parabolas, and it's also true for hyperbolas. If it's true for parabolas, then it's also true for hyperbolas and ellipses. Yeah?
Yeah, well, there is another notion which I'm not sure of. I'm not sure of. The P1, 2, and 3 are on one side of the ellipse, of the conic.
Okay.
Q1, Q2, Q3.
That's an interesting thing.
I don't know where.
So if we have 3 points on a conic, then we cannot say whether one point is between 2 other points. If we have 4 points on a conic, we can talk about separation. In fact, there is such a notion as the cross ratio of 4 points on a conic too. Okay. Yeah. So I'm pretty sure that you can. There is a kind of cyclic notion. I don't know how to express it better, but you can say that they are in this cyclic order: P1, P2, P3, Q3, Q2, Q1. But there is no starting point. I could start here, and I could use clockwise or anti-clockwise. But then I think
something like 2 points that are separated by 2 other points, and you draw the line between that and something like that.
So I think we can say the following, I guess. We could say that if we take P2 and Q1, then P1 is on one side and this is on the other side. We can say that.
Separated by at least 1 point.
Yeah, we could say that P1 is separated from P3, Q3, Q2 by these 2 points. But we do not need it, but those are the kind of statements you can make projectively. Yeah. Okay. So maybe it's interesting to look at this. I just told you if you have 4 points on a conic, you can also talk about cross ratio. Yeah? Okay. Because, well, okay, let's kind of intuitively speaking. What is the topology of an interesting conic? It's a circle. It's a loop. It's a closed loop. We know another important thing in projective geometry which has the same topology, which is a projective line. So topologically, a projective line and a conic are the same. And in fact, you can even make an isomorphism with more structure. We could do the following. Suppose we have 4 points on a conic. I cannot ask this in the exam because not everyone is here today. I can talk about the cross ratio of the 4 points. How can I do that? Choose any other point. Take the 4 lines. Okay, now I have 4 lines passing through a point. Yeah? That is dual to 4 points lying on a line. 4 points lying on a line have a cross ratio. So, 4 lines passing through a point also have a cross ratio. Okay, so another way to do that is to draw any line, take these 4 points of intersection, and say, define the cross ratio of these 4 lines is by definition the cross ratio of these 4 points. If I do that, I have to check that if I take another line, I get the same result. Why do I get the same result if I choose another line? So this is well defined. So there are 2 ways, equivalent ways to define the cross ratio of 4 lines passing through a point. You could say, well, dualize and take the cross ratio in the dual situation. Or maybe more geometrically or more elementary is take any line, take the intersection points, take their cross ratio. Doesn't depend on the choice of this line. Only depends on these 4 lines. Yeah? Okay. So now, given A, B, C, D and a point P, we can talk about this cross ratio. Okay, now we are going to move P to another point, P prime. And we look at the cross ratio of the 4 lines from P prime. How do you think those 2 cross ratios are related? The cross ratio of these 4 lines and the cross ratio of these 4 lines. Any guesses? Yeah, the same. Excellent geometric intuition. And now, okay, and now for a proof. Let's now look at the proof. So we are looking at the statement we have, or the conjecture, that this cross ratio depends only on the points A, B, C, D, but not on the point P, on the conic. Question, is that a projective statement? It involves the notion of conic, points lying on it, and cross ratio of 4 lines. Projective notions. So it's a projective theorem. So to prove this projective theorem, we can apply any projective transformation we like. Now, the good news is all interesting conics are projectively equivalent. So we can assume, without loss of generality, that the conic is a standard circle. Yeah? Okay. Now, if this is a circle, then we have the theorem of constant angle. This angle here is the same as this angle here. Yeah? It's the theorem of constant angles on the circle. Okay. And then we use the fact that this cross ratio can be expressed in these angles. And that's QED.
What to do with quick? How can you express cross ratios and angles?
So the cross ratio of A, B, C, D, or the cross ratio of the lines, then this is the cross ratio of 4 points on a line. This is the dual cross ratio of 4 lines through a point. By definition, they are the same. It is it's very similar. It's a number times a number divided. It's a sine times a sine divided by a sine times a sine. This corresponds to C minus A. Yeah? C minus A. So it's this angle. So it's the angle APC. Yeah?
Yeah, I can.
And so on.
I can fill in the blanks now, but I was just.
Etc. So the second, well, then you have to check the other one. Angle BPD. And similar here. Yep. This is an interesting exercise to prove this. how can you... So this is in fact an exercise in Euclidean geometry. This was defined as C minus A